this operation, Matt James from Australian National University. Okay, Matt.
Okay, thank you, John. Like Robin, I'd like to first of all begin by thanking the organiser, especially John Goff. I think he was the primary champion of this 4-week activity, as well as the other members of the organising committee. So it's really wonderful to have this opportunity, and also to thank the Newton Institute for hosting this event. I think it's really very important, and I think it'll give a real boost to a sort of an important and growing area of in the intersection of mathematics and physics and engineering and so on. Okay, so just to contradict one thing that Robin said is that not everyone in the room is a physicist, and so in fact my background is in mathematics and engineering, but I've done a lot of quantum stuff over the last decade or more. In fact, when I first started doing quantum control in the early 2000s, I think I had conversations with people like Andrew Doherty, and I did some initial work, and I kind of had the sense that at the time we were working with master equations and quantum operations, and at the time I hadn't learned of it or heard about the quantum stochastic calculus, but I kind of felt that there was something missing in the viewpoint that's quite common in quantum optics now. We're using master equations all the time for your modelling and your tools. And anyway, so I think Andrew pointed me in the direction of the QSDEs, which I guess is now called the SLH Formalism, according to John anyway, I guess, and Hideo and other people. So I think it really is very important, in fact, that the QSDE framework was developed, and it really does play a very natural role. So in classical engineering, of course, stochastic processes play a hugely important role, as you know. Wiener processes and filtering and all these things have a very rich and long history. And I think the QSDE framework that Robin and Parthasari introduced together with Gardner and Collett in New Zealand play a hugely important role, I think, in the development of the engineering aspects of quantum technology. I think we're just starting to see the beginnings of that now, I would say. Okay. All right, so John asked me to give this kind of tutorial discussion. I hope it's going to be a tutorial anyway. Excuse me. So what I'd like to do, first of all, is to give a little bit of orientation about the kind of modelling that might be needed for the development of quantum technology. So this workshop, as you know, it refers to the engineering of quantum systems, right? And so that's quite different to the paradigm or the normal mode of operation in sciences. I mean, science is basically concerned with discovering and understanding nature, whereas engineering is concerned with, building new things. It's concerned with designing things and analysing things like that. And so the tools that we might need for engineering new physical systems might be different from what techniques have been traditionally used for just analysing them, I think. And so once again, if you look into engineering, there's a huge set of tools and techniques and methods developed over many centuries for doing exactly that. I guess it's part of our challenge now to try to address these issues in the quantum domain, I guess. So I'd like to give a little bit of motivation, talk a little bit further about the SLH formalism, picking up from where Robin was speaking. I'd like to say a few words about feedback control, because that's a topic that often comes up in meetings like this, I guess, to try to clarify what feedback really is, and then to go on and talk about the theory of quantum feedback networks, and some examples that I've been developing with John over the last maybe 8 or 10 years, I guess, now, I guess. Okay, so let's, I think a good point to start is to illustrate the kinds of challenges that we face, is looking at the transistor, which, as many of you know, in the late 40s was a very crude physical device, an amplifying and switching device, which is now being used, of course, in very important commercial products like iPhones and computers and things like that. But this transition from the basic devices to these highly engineered systems did not happen overnight, right? This took, well, quite a few decades, right? 50 years or so, right? And I guess I'm not quite sure where quantum technology is at the moment, but my sense is that we're still kind of at this kind of very early stage. Would anybody agree or disagree with that? Andrew, you're nodding your head up and down, and you're part of an engineered quantum system research centre, aren't you? So that's kind of where we are at the moment, I guess, which makes it very exciting for us as researchers and full of opportunity, I think.
I don't think anyone's watching in the southern hemisphere, so we can say.
That's right. That's right. But to get from here to here requires a whole lot of new methods and techniques, I guess, and that's what I'm trying to point out here. So we need ways of describing not just how the single devices operate, but how whole networks of such devices would operate, how to manage that in terms of software infrastructure and things like that, trying to look at different hierarchies of generalization and abstraction and so on, all of which are very commonly used in everyday engineering. So for example, a very rough sketch of an engineering design process can be seen on this slide here, where at the very top level, which I might call the functional level, you have the level where you're just describing what you want your system to do. So in the case of a phone, you want to be able to talk to people, you want to be able to get your web browser working, you want to do your email and things like that. Those things are all described at a very high level. But at the low level of the silicon inside the chips inside the phone, of course you've got lots of low-level detail. Okay, and in between these two extremes, of course, there's lots of intermediate levels. For example, the circuit level here, where you might represent some of your parts of your system in terms of circuit diagrams. Also, one thing I want to point out here is that all of these issues at the device level are really important for the systems integration. So the ways in which, oops, pressed the wrong button here. The ways in which engineers present and develop models at this very low hardware level is typically one that has network issues in mind. So for example, how many interconnections can the device accept, for example? So the fan in and fan out, these are network issues. And also at the low physical level, there are many dynamical issues. They're all physical systems that evolve in time. They're not just discrete transformations. Okay. So I guess what I'm trying to say here is that as we start to develop quantum technologies, we need to look at different kinds of models at different levels of abstraction. What you may do at a very low physical level is not necessarily the same as what you might do at a much higher functional level, or even in the intermediate levels in between. Okay. So here I've got, again, the picture of the transistor. And I've got a few different models for this. So as you know, the transistor is a semiconductor material with electrons and holes that move around. So I think most students who learn, oops, again, I'm pressing the wrong button here. Most students who learn something about semiconductor electronics will learn about the diffusion equation and how electrons and holes diffuse through the material. So it's a relatively low level of physical description. But at an operational level, at a higher level that you might use when designing a circuit, you would just simply write down a relationship between the currents for the base and the collector, for example. This is just giving you the current gain, which is a really simple relationship at a higher level of abstraction than what you would have at the lower physical level. Another example of this is operational amplifier. So again, you can look at very low physical levels and describe the semiconductor material. But the operational amplifier itself, of course, is really quite a large, complicated network of transistors and resistors all interconnected together. And so engineers typically don't analyze these circuits directly for every application, but they have simplified models. And in particular, when the operational amplifier is in a feedback loop, then we have a very simple relationship depending on the resistor values, which allow us to make very robust amplifying devices. So one of the issues here is that the component values and the parameters for these physical systems can vary quite widely. So both during manufacturing, temperature, all these sorts of things can cause these parameters to vary quite a bit. And so you need to have a design which is going to be robust to the variations in those parameter values. And so that's one of the fundamental roles of a feedback system like this, is in order to achieve that robustness characteristic. And so this basic this basic voltage gain relationship is one that is largely independent of the natural gain of the amplifier, but largely dependent on the values of these resistors, which are much more robustly determined. Okay, so switching now to digital circuits. I guess at the top here I've got an example of a classical combinational logic diagram where we have a bunch of AND gates and OR gates interconnected together. That's called combinational logic. We have some inputs on the left and some outputs on the right. And this performs the basic operations of AND and OR and things like that. And so when I look at the quantum circuits in quantum computing, the circuit diagrams that I see look very much like these combinational logic circuit diagrams. Okay, where we just have a sequence of quantum gates, some inputs on the left and some outputs on the right, and we move through the diagram from left to right. So it looks very similar to a classical combinational logic diagram. As far as I am aware, this kind of circuit diagram is, I guess, the dominant paradigm for considering quantum computing. I guess quantum computing has yet to evolve further ways of representing systems. So in particular, I want to point out that one of the basic types of systems in a classical computer is a sequential state machine where we have a dynamical process where we have states and then we have transitions between those states depending on the values of the inputs. And so the basic architecture is to have some storage elements together with some classical combinational logic. And then this system iterates through its behavior, so changing state depending on the values of the inputs and the outputs. And so engineers who are building digital systems will generally work with these classical state diagrams where the combinational logic that I mentioned previously is just part of, but not the whole story for these systems. So an important example of that is the flip-flop. So the flip-flop is perhaps the most basic memory element in a classical computing system. But it's a state machine, so it's able to remember values, and it evolves in a dynamical fashion. So in fact, in order to understand how the flip-flop operates, then we need to, in fact, consider not only dynamics, but also feedback. So it's a dynamical system. When the inputs R and S change, then those changes get reflected in a dynamical fashion. As the input signal at R changes, the output values will change, and those outputs get fed back to the inputs that you can see over here on the left, and that causes a resulting change. So to understand how a flip-flop works, whether it's going to keep the state value or store a 0 or store a 1, it really depends on this feedback, which is a dynamical process. So dynamics and feedback are fundamental to the operation of flip-flops, which are some of the most basic elements in classical computing. And so what I don't tend to see, I guess, in quantum computing is analogues of this. And so I'm making these points really to sort of draw out some observations from my background, which is basically from mathematics and engineering over my career. And when I look at quantum computing, I can see quite a bit of missing things. And so that means there's a lot of work to be done in the future. So quantum computing, as many of you know, is beginning to evolve. And there's been a huge investment of research in the area over the last couple of decades, I guess, and still a lot of work going on. We've still yet to realize any really significantly useful quantum computing system, I guess. But an example of that would be the scalable silicon-based proposal of Kane, I guess, in the late 80s. And that's something that people are seriously working on at the moment. Okay, so also in order to address issues of robustness that I mentioned before, in quantum computing that issue becomes even far more serious. And of course, as many of you know, there's quite a sophisticated theory of error correction, and architectures have been developed with that error correction in mind. Okay, so I guess at the moment what I'd like to mention also is that throughout the electronics industry over the last few decades, I guess a lot of software tools have been developed in order to help the design process. designing a chip that goes in your iPhone is a really complicated process, right? You can't do it on the back of an envelope. You can't use it using physical intuition. You've got to have systematic design tools in order to do that. And so there's so for digital systems, the HDL is an example of what's called a hardware description language, which is part of some design tools which are used routinely in the digital electronics area. And I want to mention that Tezek, I guess, from Stanford will be talking about a quantum development or version of this, the HDL, in his talk in the next week or two, I guess it is, I think, John. Okay, so this is a screenshot of some of the software that's routinely used by engineers in digital systems. So this is from a Xilinx system. So we have a long way to go to get to this point for quantum technology, I think. Okay, just a few more words about the development of modern electrical circuit theory. So of course, the circuit theory that engineers learn about and use in their daily work is based on the underlying physics, right? The physics happens first, and then people discover how to use that in a systematic way, where they can build radios or amplifiers or mobile phones and things like that. And the whole theory of electrical circuit theory, I guess, involves a whole range of things, from device models, rules for interconnections, and methods for synthesis and simplification and analysis. And so one of the really important things I want to underscore here is the synthesis issue, which, as I mentioned before, is something that's characteristic of engineering. We want to actually build something to achieve a particular purpose. On the analysis side, which is taking a potentially complicated system and having an equivalent circuit representation. So that's something that's very widely done in engineering, is to take something that's complicated and to replace that complicated model or complicated description by something that's even simpler. So Thevenin's theorem is a well-known theorem in circuit theory that really just is a way of describing the linearity of a circuit. But nevertheless, such representations are hugely useful in describing electrical circuits. This is just an example. On the realization side, it may be desired that you wanted to design a filter to pass through signals of a certain frequency and to attenuate signals, in this case, that are high frequency. So you may want to get rid of some high frequency noise in your electrical system. And so you may specify that in terms of a frequency response diagram. So the horizontal axis here is frequency, and the vertical axis is the magnitude. And so you'd like to be able to design a circuit to actually realize this physical behavior. So we can think about this as being sort of a functional description of that system. We want to pass these frequencies and stop these frequencies. And so lots of techniques have been developed in engineering in order to do this. And this is an example of a circuit diagram that may result from the application of those design techniques until ultimately you go and build up that circuit in your laboratory. And so this is what I mean by synthesis, where you're going from a statement of purpose in some sense to an actual physical device. And that's quite the opposite of traditional science, where you're given a physical system like a star or whatever, an atom or whatever it is, and you want to understand how it works. We're kind of trying to go in the opposite direction. So what are some basic requirements then of a quantum circuit theory? So of course it has to capture the quantum physics. We can't just take classical methods and try to generalize them naively, right? We have to fully respect the quantum physics. And this is where I think that the framework of the QSTEs that Robin was talking about is really important, I think, because it captures the physics in a way which I think makes it easier to consider problems of analysis and synthesis, at least in my experience. Okay, so we have to be able to represent various kinds of components that we may encounter. We need to include mechanisms for noise and dissipation and uncertainty, things like that. Of course, if it captures the quantum physics, it will also capture whatever canonical structures that one may have. If you form a network of components and you follow your network rules, it should also be, again, a quantum system, so it should be closed in that sense, or recursive in that sense. We need to have efficient methods for representation and interconnection and manipulation as well as physical realization. Okay, so there are really, what I want to emphasize here is that what is needed, I guess, are efficient methods for systematic analysis, design, and synthesis. So I emphasize here systematic. If you're going to produce a very large system, you can't just use seat of the pants intuition, right? Okay. So moving on to the SLH formalism then. So I guess as Robin was saying in his talk, that I guess the QSGEs can give you dilations of open quantum models, master equations. And so that's my kind of starting point here, I guess, because that's a very common object in quantum optics that people work with routinely. So here we have a state rho, which evolves according to this master equation. So we have a dissipation term and a Hamiltonian term. And so, of course, there are two key parameters here, right? The self-Hamiltonian of the system, H, and the coupling operator, L. So the coupling operator, L, describes how the physical system interacts with its environment. So it might be an optical field, it may be a heat bath, whatever it might be, right? Okay, so this slide, I guess, has just got some of the boson fields again from the previous talk, but I guess I've expressed things in a sense in the white noise sense. So even though there are technical problems with looking at derivatives of Brownian motion, for example, it's still possible to at least formally do that in some sense. Okay. So the main thing I want to point out here is something that Robin didn't talk about, I don't think, and that is that the input-output character of the open system models. And so the idea, I guess this was highlighted a lot by the work of two New Zealanders, Gardner and Collett, around the same time that Robin and Passari were working, I think. And so the idea is that we have a system, in this case, in this picture here, it's just an atom. It's interacting with a vacuum, and then it's emitting a photon. So this is, again, of course, one of the oldest problems of quantum optics, emission of a photon by an atom. But we can regard oops, keep pressing this button. You can regard the input as being the electromagnetic field in the vacuum state before it's had a chance to interact with the atom. And so we can think about that as being a wave coming in and hitting the atom. The wave then hits the atom and then scatters and giving us an emitted photon. And so that encapsulates a kind of a traveling wave, I guess, picture here, where we have an input coming in from the right, hitting the system, and then being bounced back.
Yep. Sorry, by vacuum you mean no photons? Yeah, in the vacuum state. And then no atoms, or? The atom would be in the, say, an excited state. Yeah. Okay. So when the atom interacts with the field, it has an opportunity to pass some information about what state that atom is to the field, right? So information is transferred from the atom to the field in this input-output manner. So that's a hugely important paradigm. So a lot of the techniques that are used in engineering, but not all of them, of course, but a huge number of techniques that are developed in engineering are based on this input-output paradigm. So if you pick up a textbook on, say, control theory, the vast number of techniques that have been developed over many decades are based on input-output models. Okay, so the next thing I wanted to introduce was the S parameter. So we're talking about SLH formalism here. So we've talked about the L and the H, but the S, which doesn't appear in the master equation. So if we just go back a few slides here, there's no S here, right? So the S really becomes more important when, for example, you are considering a network with more than one component or more than one field. So an example of getting an S is the unitary operator corresponding to a beam splitter. Okay, and so that's an example of where the S comes from.
Another example of the S may be a phase shift. And if you're just looking at a single system, a phase shift at the input is not going to make any difference, right? Because it'll, the phase shift and its conjugate will cancel out. But if you're looking at an interconnection of systems, then those phase shifts can get picked up and they do become very important. So the S is really important, it can't be ignored. Okay? All right, so we can specify our open system by these three parameters, S, L, and H. And here I've just reproduced the Ito table that we saw in Robin's talk, and the Schrödinger equation written with the U on the right-hand side there. And I want to emphasize here as well that calculus, as you know, has a very long history going back to Newton, and it's a great pleasure to be speaking here in the Newton Institute, I guess, right? But calculus was invented for a reason, to simplify calculations, right? We could have done all of physics with discrete time calculations if we wanted to, I guess, but of course it's much more convenient to have an infinitesimal idealization, and so it has a very long history in mathematics and physics. Also, stochastic analysis has also a very long history in science, and going back to some of Einstein's early papers on Brownian motion, for example, are really very important. And so it seems to me that the quantum stochastic calculus will have a hugely important role in quantum mechanics and also quantum technology as we're moving forward, I think. Okay, so these are just the equations that you've seen in the previous talk. So when we do have a Heisenberg evolution using the QSTEs, then we can always take expectations and recover the master equation, right? And so the SLH formalism allows us to easily write down the master equation when we want it. So we might want the master equation, for example, we want to do a calculation. We want to program on the computer and do a simulation. You need a master equation. Master equation plays an important role at that point. But I'm not sure it plays the same role at the fundamental level of physical modeling. Okay, so I also want to mention that the theory of quantum filtering also makes use of the SLH QST formalism. So I won't go into any detail on that in this presentation. I guess John will pick that up in his talk later in the week. But working with QSTEs is the natural way of setting up quantum filtering problems. Also, an important comment on that, I guess, is that when we have our SLH QSTE type evolution, if you think about it here at some fairly abstract level, I guess, driven by the quantum Brownian motions that we've been hearing about, if we take the quantum expectations of this and we recover the master equation, as I've just been mentioning, but also if I take the quantum conditional expectation, then I can recover the quantum filter. And so the quantum filter becomes a very natural implementation of conditioning when we have a commutative set of observables that we want to condition on, such as a photo current record in an experiment. And when we take the classical expectation of the quantum filter, we recover the master equation. So all of these ideas are very natural to engineers, I must say, because the quantum filter goes back to Stratonovich and Kushner in the late 1950s, early 1960s. We've been using techniques like this for many years. And that's why when I started doing quantum control and saw so many publications dealing with master equations, quantum operations, I felt that there was something missing. Because I couldn't, at that time, I wasn't aware of this SLH formalism. Okay? But it's there and it's hugely important. Just a few brief words about probability, I guess. So I guess people know about quantum mechanics as being kind of an extension of classical probability theory, right? And I guess that viewpoint is hugely useful for trying to deal with quantum technology, because after all, if we're building a quantum technological system, invariably it's going to involve interconnections of classical and quantum components. They need to talk to each other correctly according to the rules of physics, right? And so a very convenient way of understanding how all that fits together is using quantum probability theory. And in particular, classical systems can be thought of as being essentially commutative subsystems in a very natural way. Okay. All right, so just a few brief words about feedback. So feedback, like the Watt governor in a steam engine, is essentially the modification or control of a process or system by its results or effects. So feedback is a situation where some information about what the process has been doing influences future values of that evolution. And so, for example, we've heard about negative feedback, positive feedback in many kinds of systems. So that's a definition of feedback. And just to try to clarify things a little bit, so with my background in control theory, people are often interested in the different kinds of control techniques. And so the most basic kind of control is open loop. So where we have a system which is being controlled, and a control system which is just, determining some instructions for the physical system to follow. So there's no information from the physical system going back to the controller. That's called open loop control. And a lot of the literature that I see in quantum control is about this kind of open loop control. Okay? But closed loop is really where feedback enters. And I guess feedback really is probably the most important idea in control engineering. So, because it has this self-correcting characteristic. So closed loop is where we have a system that we're trying to control. Some information from that system is captured by the controller, which is then processed to determine future control actions. So we have information flowing around in this feedback loop. So there are two types. So when the system is a quantum system, there are two types of information that may flow. So for example, you may take a measurement of your quantum system to produce some classical information. That classical information may be processed on a classical computer, which is then used to determine the future behavior of your physical system. But feedback need not necessarily involve anything classical. We may as well keep everything fully at the quantum mechanical level and have quantum information flowing around the loop, in which case the controller itself is a quantum mechanical system, and all the signals in this loop are at the quantum mechanical level. Okay, and to me, this seems to me to be the area of greatest challenge in developing the theory for quantum control, is developing systematic methods for designing fully quantum mechanical coherent feedback loops like this. Okay. Okay, so moving on to the last part of the talk, I guess, quantum feedback networks. So I guess we're fundamentally talking about open systems, and the SLH is a parameterization of these open systems. But of course, it's very common in practice to have some direct couplings between physical systems. Not everything necessarily needs to be represented in terms of inputs and outputs. So you may just have two physical systems just directly coupled to each other. And so you might think about this as being a slight augmentation of the SLH framework to include some way of describing these direct connection couplings. So what I've tried to do here is to write down a parameterization of the physical system in terms of the SLMH, but I'm trying to separating out the parts of it that relate to the channels or the interface, if you like. Okay, so in a quantum feedback network then, the nodes are going to be open quantum systems. So they have inputs and outputs and possibly some mechanisms for effecting direct couplings. The branches are going to be either physical couplings in the direct case, or in the case of input-output aspects, there'll be indirect couplings, which may be, for example, freely traveling quantum fields, say optical fields. And we can think about these things as being like quantum wires, if you like. So notice that these indirect couplings are directional, inputs and outputs, whereas the direct couplings are bidirectional. Okay? So of course the direct couplings really don't add anything new mathematically. In fact, the direct coupling parameterizations can be expressed just in terms of the Hamiltonian. So you're not really adding anything new in terms of physics, but it may be convenient if you're trying to describe mechanisms by which a particular system interfaces to other systems. Okay, sorry, I pressed the wrong button again. All right. So here's an example of a quantum feedback network showing a set of SLH systems all interconnected together. And so a basic question would be, how do we combine such systems? And how do we form a model from that interconnected system? Are there any simple algebraic rules? So for example, if we have, in the classical case, if we have a pair of resistors, we put them in series, then the equivalent resistance is just the sum of those two resistances, right? So that's a very simple algebraic rule that we all learn and use. So once we get simple algebraic rules, then we open up the opportunity to automating the process, right? And so that's where the software tools come in. Okay, so for a series connection then, I guess there was some very nice work in the early 90s by Gardner and Carmichael, New Zealanders, who took the output of one system and fed it into the input of another system and worked out the equivalent system that would result from that process. And so in terms of the SLH formalism then, if you've got SLH for system 1 and SLH for system number 2, what is the SLH for the combined system? Okay. So the way to get some feel for this is to think that the input to the second system is a slightly delayed version of the output of the first system, where this tau here is just a small delay parameter. And then perform a direct substitution into the equations. And so if you write down the equations for the outputs and make the substitution, then you can pass to the limit as tau goes to 0, and you'll start to see in the output equation a product forming. So this S for the series combination will be the product of the two S's, and the L for the series connection will be the second L plus S2 times L1. Right? That makes sense, right? And we also need an adjustment to the Hamiltonian, which is this imaginary contribution. So the total Hamiltonian is the sum of the two Hamiltonians plus this imaginary term. Okay, so here's the general form for what we call the series product. So I guess John and I published this like 5 years ago, I guess, in IEEE. And so we do have a very simple symbolic rule. So if we want to form the series connection of two systems, then we just use this series product. And it has a very nice property in that it behaves essentially like a group multiplication. You think about a category of physical systems parameterized by SLH, and it's closed under this series product, which was one of the requirements that we wanted to have of a good network theory, right? Okay. Other things that we might do will be just to take a whole lot of isolated systems and to consider them as one system with, say, multiple inputs. And so we called that the concatenation product. So this is just piecing together systems without doing any interconnections, but just assembling them all together. Okay, so it's just like taking a whole bunch of input-output systems and regarding them as being one physical system. Okay. And the third construct, which is hugely important for feedback, is the linear fractional transformation. So this is where we may have inputs and outputs, where we may want to only use the feedback on some of those inputs and outputs. And effectively what we would like to do is to remove the edge here in the graph. And so that edge elimination corresponds to a linear fractional transformation. And so again, we get SLH parameters coming out from that linear fractional transformation process. So it's closed under this process. And so an early result in this direction was a very nice piece of work by Masahiro Yanagisawa in 2001, where he considered a simple system in a feedback arrangement with a beam splitter. This is exactly a situation where we need to have this linear fractional transformation being used. So if you think about SLH systems as being a category of systems, then they're closed under all of these natural network constructs. But the SLH category, if you like, is not closed under some of the limiting processes that we may consider. So for example, if you do an adiabatic elimination, you may end up with a Vogelbach transformation instead of a unitary transformation. So you can think about those kinds of systems being on the boundary, if you like, in that sense. For the direct couplings, as I said, all of that can be accommodated just through bookkeeping with the Hamiltonian. And so the bow-tie product that John and I worked on a few years ago is you take a physical operator for one system, physical operator for the other system, and multiply them together and form a unitary Hamiltonian, Hermitian term here in the Hamiltonian. And it's really, as I said, it doesn't add anything new to the physics, but it may be a convenient way of describing the direct couplings between two physical systems. Okay? So the input-output modelling, of course, makes sense when one system is very large relative to another in a sense, right? Like the electromagnetic field is very large relative to a single atom, right? That's an idealization. Okay, so I'll finish the talk then with a few examples. So this example is an example from a nice paper by Howard Wiseman and Gerard Milburn, both of whom I expect will be here at some point at this workshop, I think. So Andrew's nodding, yep. So this is an example where we have a pair of optical modes in cavities, and we have them interacting in two ways. One is internally and one is externally. There's an internal interaction through a crystal in this box here, and that's handled by this bow tie product, if you like. And also they're interacting through the freely traveling field directionally through an external set of mirrors here, as you can see. And so that can be handled very efficiently using these simple algebraic tools. You just write down the SLH for each of those cavity modes. You write down the, I guess, the full system here in terms of the series product, where we can see that, I guess, one of these cavity modes has an output which is being fed into the input of the other cavity mode. Okay, so all that can be done symbolically. So I guess Mathematica would be a good tool for these kinds of things. And so again here I was trying to draw a picture here which wrote down a simpler sort of equivalent circuit representation, if you like. So there's an SLH for this whole system which can be just automated, right? And once you've got the SLH parameters for that network, if you want to write down the master equation, you can, right? You just press a button, it writes down the master equation, put it into your solver for solving the master equation, and you can do your simulations. But the physical modelling is all done at the level of at the SLH level here. Okay, so that's very much in the spirit of widely used engineering methods. Another example is so-called direct measurement feedback. So again, this is an example from one of Howard Wiseman's papers from the early 90s, where we have a quantum system with an input and output. The output field is monitored. So here, for example, with photodetection, that produces a photocurrent I. That photocurrent is then multiplied by a gain, just a constant value, forming a control signal, which is then goes back to modulate the physical system. Okay? And so this whole arrangement can be very easily described in terms of the SLH formalism. Okay? Because what we do is we write down a description. So, so I guess in their system, H naught here is the natural Hamiltonian of the system, and the FC here is the part of the Hamiltonian that can be modulated by a classical control signal C. So what we do is we break that system down into two pieces. So here I've got the concatenation product, right? So we regard that as being an open system with a single channel, concatenated with a second open system, where the second open system has an S operator, That S operator is now capturing the effect of selecting the gauge process of the output field. Okay? So when you do that, so the S here turns out to be e to the minus I times F. And when you plug in the, I'll just switch to the next slide where you can see it more easily. You take the output of the first system and put it back into the second. So that corresponds to exactly this loop here at the bottom of the diagram. Then we have an application of the series product, and we get very easily the SLH parameters for that feedback system. Once you've got those SLH parameters, you press a button, you've got your master equation, press another button, and you've got your simulations, right? Very straightforward. Another example, again, going back a decade or so, was some work by, I guess, several people, including Howard Wiseman and Hideo Mabuchi, I guess, who will also be here fairly shortly. And so they were considering the problem where the detector, the photodetector in their physical system, monitoring their physical system, was not perfect. It may have had a finite bandwidth. And so essentially what you were trying to do was to do some filtering or estimation on the basis of a cascade of a quantum physical system together with a classical system. And again, that problem can be very efficiently expressed using the SLH parameters. And the main thing one needs to do here, I guess, is to express the classical subsystem, which is a classical system meant to describe the finite bandwidth of your detector as a commutative subsystem of an SLH system. And once you do that, then you can just apply the series product. And once you've got the SLH parameters for the complete cascade system, then again you press another button and you can write down your filtering equations, because the filtering equations are determined exactly from the SLH parameters. And that this is what they would be in that case. And so this is an example of, remember earlier in my talk I mentioned the usefulness of thinking in terms of quantum probability, where we think about the classical systems as being commutative subsystems of quantum systems. And so here this classical subsystem now is represented as a subsystem of an SLH system, and then I can apply my the series product to get the connection between the two of them. Once I've got those SLH parameters of that combined system, then it's a straightforward matter to write down the filtering equations. Okay? So I guess that brings me to the pretty much to the end of the talk, I guess. I do want to mention, I guess as a prelude to Nick Tezek's talk, that he'll be talking about what they call QHDL. So QHDL is a quantum version of the HDL hardware description language that I mentioned earlier. So that has been developed in Hideo Mabuchi's group in recent years. And I guess Nick will run through a description of that and related software tools. And so we're beginning to see some of the high-level engineering tools that we need for quantum technology design starting to emerge. Thank you very much.
Okay, plenty of time for questions. Peter? Yeah, I have a question that probably will reveal my ignorance of the subject. So the S is a unitary scattering operator, but why can you not encode that into H? Because if I understand correctly, so your H in SLH is your Hamiltonian for your free evolution, and then your L is your Lindblad operators.
Yes.
And then S is some scattering. Why, if S is unitary, why can you not put that in H?
I guess it's trying to describe how the field is coupling to the system, right? And so it's got to have some origin as an interaction between the field and the system.
And so S is acting on, not on rho.
Acts on the input field. I think that's the way I understood it now, finally.
Yeah.
He acts on the input field before he enters the equation.
Yeah, like in a beam splitter.
It decides what couples to the environment.
Okay. Yeah.
Yeah.
All right.
Okay.
Thanks. No, thanks.
The danger with that bit of illumination is that the S doesn't necessarily have to be constant coefficients. They can actually be operators and operators on the system.
Yeah.
Yeah.
That's right.
So they can actually evolve as the system's being driven itself.
Okay.
Yeah. Yeah, so you could have a boom splitter with a transmission coefficient that's modulated by a signal, for example.
Yeah, yeah.
That signal could have resulted from a measurement of a quantum system.
Yeah.
And so you can regard that in this operator setting.
Right.
Yeah.
Andrew.
You made a very brief comment that I wondered if you might expand on, and this was to do with adiabatic elimination, which you might hope would be another kind of map between SLH systems.
Yeah.
And you said something about how you can end up at the edge of the set, and you would end up with a non-unitary operator at some.
Yeah. So what I had in mind there was, I guess if you look at some of the models for, say, amplifiers, degenerate parametric amplifiers, and then you remove the internal cavity degree of freedom, and you get a Bogoliubov type transformation relating the input fields to the output fields. So the Bogoliubov transformation is not of the other unitary S, so it's like an extension of that in a sense. So yeah, we looked at yeah.
I mean, with the adiabatic elimination, there are some results of Bolton, Van Handel, and the Silverfarb, where they show you can stay in the same category of QSDEs if you set up the elimination problem correctly. There you don't go outside of this category. The problem Matt's thinking of, I think, is when you're looking at problems which are specifically representation specific, so you're working, say, in the Fock representation, that you go to something that's limitingly in an equivalent representation. So for instance, something like a Bogoliubov transformation, which is okay in finite dimensions,
somehow on
but
the
in
field.
infinite
Something
dimensions.
that's
That's
going to turn a vacuum state into a.
That's right.
The vacuum state of the field into a squeeze state.
That's
of the
right,
field.
exactly. Yeah, squeezing is a classic example of this.
See, not all infinite dimensional.
So it's for every mode on the field. So yeah, so it would be okay for a single mode, but it's changing the Hilbert space if you apply it everywhere to the input field.
There was something called Shade's theorem, which shows you when you can't unitarily implement the symplectic transformation. On infinite dimensional spaces, it is an issue. There are equivalent representations.
So that's
but if you're
for
just
non-
looking at the SLH coefficients, you can have a limit which would actually lead to the S being replaced by something non-unitary, but corresponding to a Bogoliubov transformation.
Okay, I understand.
But you can see, even that example of direct feedback, the importance of having the S, and the importance of having S as an operator of the system. Right?
But any finite number of modes will do. But implicitly in these input fields, you have infinite continuous.
Yeah, we
Okay, okay.
continuous variables.
That's right. Yeah, so generally the emphasis of our use, so far at least, of the SLH formalism has been to capture dynamics and feedback, things like that. So things that I think are really important as we want to move forward in quantum technology, and things that I think are largely missing in a lot of the quantum computing research that I've seen.
Sorry, I have one other question. So when you have this S matrix, you can end up with a term in the Heisenberg equations of motion for an observable X that has this term that depends on S, and the coefficient is this gauge operator.
Yeah.
Which, as we heard earlier, that's if I've got a zero temperature mode. So if I go to the, I'm just a little bit confused about what happens if I try and do this at finite temperature. So in that case, as we were hearing earlier, you could model that with this non-Fock.
Yeah.
And so in that, and the d lambda doesn't exist.
Yeah.
I would have thought physically something like the S matrix should exist. What's going on there? I mean, does this SLH formalism really need us to be thinking about zero temperature input fields, or?
Not in general, but you have to be
careful about how you use it, I guess, right? So putting it into a positive temperature and trying to measure the number operator, of course, doesn't make sense.
Yeah.
So you've got to be guided by what's physically sensible, I think.
So your concatenation rule is strictly zero temperature. So the concatenation for XS, but you don't even consider finite anyway.
I guess my feeling is that you would build up what you would need for non-zero temperatures by using, for example, the Iraqi-Woods representation that John mentioned, and then be careful about making sure that you define objects that make physical sense. Yeah. So if you wanted to treat, say, for example, a filtering problem with, squeezed fields, for example, you would have to use the Iraqi-Woods representation. So another area where the S becomes important in the master equation even is when you consider input fields that are not in a vacuum state, but in, say, for example, a single photon state. So, for example, if you have a continuous mode, single photon input, then the master equation definitely depends on the S. But in the vacuum case, of course, the S drops out. I think the way to think about these things, I guess, is that the quantum noise representations are really sort of fundamental canonical representations, and you can build up more, like colored noise, you can build up by passing it through a filter, and you can create photons by emitting them from a system and things like that. And so you want to go back to that sort of fundamental level. And again, that's in the spirit of a lot of engineering techniques, right? If you go and study about the Kalman filter, for example, chances are the author would have presented it for, white noise with unit variance and so on. But of course, your real physical problem in your aircraft or whatever has got colored noise, and so you have to go and build a filter to represent that colored noise. And so I guess our SLH formalism is at that abstract level, and then you want to map that to a real physical situation, whether it be single photons or squeeze states or whatever it is, you've just got to build the appropriate representation, I think.
Any further questions? Madeline.
I didn't understand your remark about the end with the filter. So is the idea that you can describe filtering also as a concatenation, as a network?
No, it was just in that example. So I made a remark earlier on, I think, that quantum filtering depends on the SLH formalism, right? You write down the QSTE for your system, you work out what measurements you want, Hamidine or photon counting or whatever it is. And then, of course, with Blavkin's results, you've got the filter, right? But they all depend explicitly on the SLH parameters, right? And so what I was trying to say in this example of realistic detection is that, hang on, now we have a quantum system and a classical system together in the same problem, right? So if we had the classical system by itself, then we know how to do filtering because we just go back to Kushner and Shonovich from 1960 and write down the filtering equations, right? Or the Kalman filter if it's linear, right? If it's a quantum system by itself, we can just look at Blavkin's theory, right? Okay? But when we've got the two of them together, we've got to put them on the same footing. So the way to put them on the same footing, we can't go down to the classical world because we're getting real quantum mechanics, right? So we've got to bring the classical one up to the quantum level correctly, right? And so that's where we're using the representation of this classical system as being a commutative quantum system. Okay? So then you're in a position where you can use the series product. So the series product will give you the parameters of this whole equivalent system. Once you've got the SLH parameters for that whole equivalent system, then it's straightforward then, given Blavkin's results, to write down the filtering equation. But that's what I was meaning.
Here in this equation, where is the input I?
Yeah, I guess that's meant to be the photocurrent. Yeah.
Is it dW? Something like dW minus the trace of L.
Yes, it will be. That's right.
Something like this.
Yeah, so this will be the output of this quantum system. Yeah. Yeah, this diagram probably came from the paper, which the details aren't on the slide, I guess.